What type of charger does it need? What type of charger does it need?
No, it's not USB-C.
Is it the round one?
Yeah.
I have it.
This one? I
Here.
don't know, I'm pretty sure it's like only like,
You can try.
I can try it.
Here.
You can get like a...
Nope.
Okay.
Yeah, it's like an Asus. Anybody who's got Asus? That's okay, I can just do it on the even though the podium is detestable. All right. Let's see here. There we go. Sorry for the delay, folks. So, we're continuing on with our journey into the wonderful realm of recursion. At some point, my laptop is going to die, and then I'm going to switch to using the podium computer. Where were we? We were talking about the Fibonacci sequence. Yes. So, essentially, the next few slides are a recapitulation of things which I demonstrated via demonstration last time. But essentially, the thing to understand about the number of iterations that we use, the number of recursive calls to the Fibonacci function is it's proportional to the square, not square, 2 to the power of the number which you're putting into the function. This is generally considered to be a terrible runtime. So, one brief note on infinite recursion. So, in the same way that with a while loop, if you forget to increment the index or you've messed up the condition somehow, it's possible, well possible, to end up in an infinite loop. There were, I think, a couple of people on the test who got infinite loops and didn't understand that they had infinite loops and were wondering why their code wasn't running. And they got the little star in the square brackets on Jupyter. That is an infinite loop, my friend. It is tying up your computer resources infinitely. Infinite loops in Python are a worse problem than infinite recursion. The problem with recursion in Python is that you will eventually hit Python's inbuilt recursion limit of about, I think, 5,000 recursive iterations or something of that nature. Basically, Python has built into it a hard cap on the number of recursive calls it can make, thus limiting the impact of infinite recursion when it does occur. In general, though, if you do hit that 5,000 limit and you're not doing something where that would be, even a little bit expected, you're probably in infinite recursion territory. So there are a couple of ways that you can get into an infinite recursion. One is by forgetting the base case, or forgetting to do the base case, or not doing the base case properly. Remember that the base case is the thing which terminates the recursion, right? It is the thing that does not make the recursive call. Therefore, if your recursion is infinite, the most likely problem is in the base case. That being said, in our particular iteration of the Fibonacci sequence, you'll notice that we only hit base cases when n is equal to 0 or 1. If we have set up the iterative case so that, in theory, we're skipping over the base case, right? So if you imagine a definition of Fibonacci which would have something like n minus 4 or something like that, one of those recursive cases will jump over the base cases defined for 0 and 1 and just continue on into the negative numbers which of course is a problem. The Fibonacci sequence is not defined for negative numbers, so there you go. So, what way would you choose to avoid the problem of infinite recursion in this manner? Anybody have any ideas? How could you avoid traveling into negative space? Yes?
If n is less than 0, then return 0.
Sure. Or some other similar variation. So, right now we are excluding half of the integers by not giving any specified behavior for the negative numbers. What you could do is just introduce a case that deals with the negative numbers. One thing that you could do, which would probably be correct, the most correct way of doing it, is if you receive a negative number as an input, raise a domain error, or give some kind of exception that indicates you're trying to ask for a Fibonacci number that doesn't exist, right? That way, even if you do screw up your iterative case in such a manner that it goes into negative numbers, you're going to get a strange error and not just it going infinitely, right? Make sense? Defensive programming. Defensive programming means defining things as explicitly as possible and always thinking about the entire domain of the data type that you're working on, right? Don't let the else case pull too much weight, right? Does that make sense? A little bit of sense? So let's talk about the manner in which we might measure the efficiency of an algorithm. In general, there are two approaches to the measurement of the complexity of algorithms. You have the theoretical approach and you have the practical approach. You might also call this the theoretical and the empirical methodologies. In general, software design is not as amenable to empirical methodology as some of the harder sciences, shall we say. Things like chemistry and physics. In chemistry or physics, if you perform an experiment, those results are repeatable if all interfering variables are held constant, right? That is the purpose of the laboratory, to provide an environment where all other variables are held constant, right? Software is not so easily measured. How fast, just taking into consideration runtime, because it's, runtime is a very important aspect. The amount of time it takes an algorithm to run is dependent on many, many, many factors. It is dependent on which computer is executing the program, the particular hardware devices that computer has available, the model of the CPU. It has to do with the operating system that you're running. It has to do with whether or not Windows is updating. It has to do with all of these different factors. That's why the practical approach, which is simply to run the program and measure its runtime. This is the approach we were using with the Fibonacci numbers. This is not going to give you very good generalizable results. Me running Fibonacci on my computer does not necessarily say anything about any of your computers, because my computer is a very specific organism, right? So, this is why, in general, the runtime of algorithms, at least from a early bachelor's degree perspective, shall we say, the runtime of algorithms is primarily derived theoretically rather than empirically. That is to say, We examine the algorithm itself, draw theoretic conclusions from the structure of the algorithm, and use those theoretic conclusions to classify the algorithm. Primarily, we are interested in classification. So, in general, we can talk about both runtime and memory complexity, but perhaps we should talk about what we mean by complexity. In general, the thing that we're concerned about is not how much time it takes to execute, fib 40, right? It might be an interesting benchmark to be able to compare different computer systems, but we're not interested necessarily in how long it takes to sort 100 items, right? What we're interested in is how much longer it takes to sort 101 items than it did to sort 100 items. We want to know how quickly the runtime and the memory usage is growing as compared to the number of inputs provided, right? Does that make sense? So, this is the problem in general is, because at least, for a great period of computational history, computers were becoming faster at a very rapid rate. If you were performing a bunch of studies on how fast it takes a Linden Series Pro from the late 80s to perform a computational task, that research was completely useless 3 years later, right? Whereas, if you base your analysis on the structure of the algorithm itself, the structure of the algorithm does not change no matter what computer is running it, right? So that's a far more stable and applicable result. But anyway, any questions? Okay. So, again, this was demonstrated relatively nicely by the laptop demonstration, but as n increases, our runtime increases exponentially with our naive implementation. So, in terms of terminology, an inefficient but simple algorithm normally has one of two names. We either call it a naive algorithm or we call it a brute force algorithm, right? So the thing that characterizes a brute force algorithm is that you are relying on the speed of the machine itself to be able to perform the computation in a reasonable amount of time, rather than doing anything, intelligent with the algorithm itself. Over-reliance on hardware, that's another way of thinking of a brute force algorithm, right? So, runtimes scale exponentially with n, very inefficient for large n, and that's large n exclamation point, not large n factorial. It would in fact be very, very highly inefficient for large n factorial. So, we've already done the idea of memoization, but these problems can be ameliorated by spending a little bit of memory to get a lot of runtime. If we cache our intermediate results, they don't need to be recalculated. This essentially turns this gigantic tree of calls to Fibonacci into a single linear run, mostly. As a consequence, Fibonacci with memoization, you can see that for much larger n's, our runtimes are increasing directly proportionally to the number of inputs, rather than being proportional to, some number to the power of the number of inputs. So for very large n, this is extremely important. Efficient algorithms are the difference between being able to calculate something and not being able to calculate something in the span of a human lifetime, as I think I've said multiple times in this class. So, I won't belabor the point too badly. So, any questions about any of that? Good. So, binary search then. Or searching algorithms in general. I'm a little okay, we haven't covered this yet, right? A little bit? Did we talk about it a little bit? Did I mentioned it? Okay, we're going to go through it in detail. I'm at this very moment, yesterday in my second year mechatronics class, I was also doing binary search with them. So I'm and we just started searching algorithms in the second year algorithms class that I'm teaching. So I'm slightly confused about what I have or haven't covered in this class. So if I'm talking about things I've already talked about, please let me know. I'm going to need that table. Thank you. I know you guys were the cool kids because you had a table, but you just have to understand your place in the hierarchy, that's all. Yeah, I can't, because I forgot my charger. So, if it's telling me it's critically low, however, I might want to. Yeah, the chalkboard. Which? Yeah. No, it's okay. I'll switch to the podium computer. How much you want to bet this thing's going to ask me to verify a code on my phone? Yeah, definitely. Does anybody want to volunteer to log into Avenue for me? All right. I promise I won't use it. I just need, if you could just bring up the slides that we're doing, I would really appreciate it. Thank you. I apologize for all of this. It's not really an excuse, but I didn't get a lot of sleep last night because I was convinced that my wife was going to go into labor in the middle of the night. Yeah, so it's not conducive to sleeping effectively. She was showing very strong signs of pre-labor for a period of 18 hours over the last 24-hour period. And then this morning the kid just decides, nah, not today. So, that's why I'm here. Anyway, so, while we're getting things set up, is it not working for you either? Okay. Okay, does anybody have, okay. Is anybody logged into Avenue right now? Because we can put it on a USB drive in theory, maybe. I don't know, does this thing have a USB slot? Jesus Christ. Yep, okay, all right. Who had their hand? Would you mind just like? Oh, yeah, that would work too. Yeah, actually it's anything. It's got like one of those great big cable octopuses. Thank you. I appreciate this. No, this will be sufficient. Yeah. I don't even like need them that much. I just need to have them. Thank you. USB-C, right? It doesn't look like it does have USB-C actually.
Does it?
No. You have an adapter? Okay, all right. I got it. Thank you.
Wait, only like one. Yeah. Temptation. The temptation is getting the temptation. Wait, what's I don't know what.
Hey! There we go.
Pushed it Monday, and I did bench incline, and then just push it to windows. I just showed it as well. And normally 50s is like no fucking problem. But
all right. Good. All right. So. All right. The boomer has figured out the technology. And thank you. So. Searching is a fairly important operation. It's garnered quite a bit of research over the years. I shouldn't have to convince you too heavily in the age of Google that what the power of being able to find data in the vast sea of data constituting the internet would be. You can become a company so powerful that you can drop the "don't be evil" motto. So, if we have an array, the purpose of a search operation can be one of two things. Either you're just simply looking for a test of membership. Is this item in the thing or not? Or you want to find the place in the data structure at which the value might be found, i.e., you're trying to search for the index of a particular value should it exist. Right? So, the most basic approach to this, which is one that actually comes up a lot more than you might think, is something called linear search. So, if we can assume nothing about the data that we are searching, where could that element we're looking for be? Anywhere, right? Because we're not making any assumptions. Therefore, to verify that the item we're looking for is not in the array, that's the worst case scenario in terms of runtime, we have to go through and check every single element in the array period. Right? That's what linear array is. You just loop through each element of the data structure, looking for the thing you're looking for. Once you find it, you don't have to look any further. That's why looking at each item is a worst case scenario and not a best case scenario. Incidentally, what's the best case scenario for a linear search? Yes, you find it in the first place you look. So, very simple, one while loop, no biggie. Make sense? Everybody could implement a linear search on a test? Can you do a for loop? Yes, in Python? Yeah. For I in rain, or for I in L, if at I is equal to K, where K is the thing you're looking for, return true, and then after that, just return false. Right? I'm pretty sure we have that in the slides, actually. Now that I think about it. So, another thing you could call this is unstructured search. Here it is. So, very basic algorithm. It's actually the best we can do without making any assumptions about the data itself. Efficient searching always... Efficient searching requires you to be able to make some kind of definitive statement of property about the values that you're searching. Only then can you do better than a linear search, right? So, one of the most basic properties that you can apply to a linear data structure is the property of sortedness. If your data is sorted, you can do more with it than if it wasn't, right? So let me just take this and very quickly sort it. This is an implementation of selection sort, by the way. There we go. My array is now sorted. You'll notice that no 2 occurs in this array, so that's our worst case scenario, right? If the array that we are working on is sorted, we can apply a much more powerful technique known as binary search. So the binary search, the reason that it's called binary search is it throws out half of the array at each step, right? It relies fundamentally on the transitive property of ordering relations, which is fancy math speak for if A is less than B and B is less than C, then A is less than C, right? If this property does not hold for the particular thing that you're trying to search, then you're not going to be able to apply binary search usefully. But you're going to be talking about something like a partially ordered set or a lattice, which you probably won't get until grad school. So, although I could be wrong about that, typing relations, some advanced typing relations like polymorphic types have like supertypes and subtypes which form partial ordering relations. So, at any rate. So, the binary search algorithm. Let's say, just for the sake of interest, that we are looking for 2 in this array, right? This is how we proceed. We examine the middle element. If there are 2 middle elements, go for the smaller one, or the one that has a lesser index, right? We examine this. In this case, we have a 4. The number we're looking for is 2. Because this is a 4, we know that nothing physically higher than the 4 can contain the 2 that we're looking for. So, we throw it out. Right? we then perform the same process on this now much smaller array. We examine the middle element. That's a 3. We're looking for a 2. So we know it can't be higher than this. We take this and we throw it out. We take a look at the middle element. This is a 1. We know that 1 is less than 2 and that nothing less than 1 can be greater than 2. So we throw it out. We have but 1 element remaining. We examine it. It is a 3. 3 is not 2. Therefore, the element is not in the array. Right? That is the binary search. It is a vast improvement over linear search in terms of runtime. Think about how few elements we had to examine out of the total number of elements in order to cycle through and find a result, right? If you took 1,000,000 elements, you can search that in 20 steps, right? At each additional step that you take in the binary search algorithm allows you to search twice as many elements as you were searching before. The one caveat, of course, is that the array must be sorted. That is, without that, it doesn't work at all. And, as it turns out, sorting is a more difficult problem computationally. I would say it's, intellectually it's about an equal problem to searching, but in terms of the amount of time it takes a computer to sort things, it always takes much more time to sort than to search, right? Even linear search outperforms the best sorting algorithms, right? So, if your data is unstructured, it does not, you don't want to sort it in order to be able to apply binary search. You just want to use linear search, right? You will spend more time sorting the data than you would ever gain by you being able to apply binary search to it. Make sense? Question?
Around how many searches would you need to perform in the future for sorting to be more efficient?
How many searches would you need to perform in the future for sorting to be efficient? That's a good point. That's kind of the thing that I wasn't saying. It does make sense to sort it if you're performing many searches in comparison to the number of items that you're sorting. You'd have to derive a formula and equate the formula. In general, the approach that's usually taken to this sort of thing, you perform so basically you don't allow the array to come into an unsorted state, right? You start off with an empty array, right? So if this is my array space, I have an empty array, right? I then take the item that I want to add, I add it, I take the item I want to add, and I add it to the array in such a way that it finds the correct position, right? And I continue to do that. I am actually inserting the elements at their correct point in the array rather than doing that all up front, or doing that all at one time, right? So what that does is it amortizes the cost of keeping the array sorted over the insertion operations. One of the advantages of this, because the array is sorted the entire time, we can use the binary search algorithm to find the correct position to insert the element, right? Or something like it. So, the insertion procedure, which keeps an array or a list sorted, can be done in logarithmic time, just like the search algorithm, right? The only problem is you have to do it n times, right? Once for each element that you're adding. So constructing a sorted array from scratch from just elements is n times log base 2n. That's the complexity of the algorithm. That also happens to be the complexity of the better sorting algorithms. Things like quick sort, heap sort, and merge sort also have n log n complexity, right? So, to insert things into an array one at a time and put them in order is basically the same thing as sorting it. You're just talking about a different sorting algorithm at that point, and that's, that still has a complexity that's worse than just linear searching. Make sense? But, again, if the number of searches that you're performing is great and the number of items, and the items don't change much, right, it can be advantageous. The way that you would say that in more formal language is if you take the runtime amortized over the number and the number of operations performed and which operations are performed, the runtime might be substantially, you might be able to get it out. This is why, there's no such thing as the universal algorithm, right? All algorithms are good in different situations. And being a good programmer means knowing which algorithm is good in which situation. Make sense? Any other questions? That was a good question. Okay, so the procedure in general, first we must assume that the list is sorted. Actually, increasing or decreasing order doesn't matter much. What it does affect is whether you're, which half of the array you're throwing away, based on the middle value, of course. But, it basically works the same way. It's like a mirror image of the same algorithm. So, we describe both by saying one of them, basically. If the middle entry is equal to the target entry, then we found it, and we need to proceed no further. If the middle entry is larger than the target, we only need to look in the first half of the list. If the middle entry is smaller, we only need to look in the back half of the list. By so doing, we divide the area of the, basically it's a refinement of the space of possible answers. Question? Okay. So the binary search. So if you it's a kind of a different way of conceptualizing algorithms, but it's a useful one, particularly the further on you go. Think about the problem as applying to a space of possible answers, one of which is correct, right? So in a searching algorithm, your array is a space of possible answers, one of which is correct, right? The binary search algorithm divides that space in half at each step. This is a similar conception to how I was hoping that you might conceptualize the make-change problem. If you consider the make-change problem, there is a space of possible coin combinations, right? Of that space of all possible coin combinations, a subset of that space is those coin combinations which add up to the target value, right? Of that space, there is a subset of that space which is the number of coin combinations that use the minimum number of coins, right? So the greedy algorithm that we did for the make-change problem, it manages to get us inside of that one shell, right? We can get a an answer which is not wrong in terms of the target value, but it does not guarantee to get us right inside that minimum coin space, right? So that's kind of the idea with this as well. That's a useful way of conceptualizing these things later on. So, good. Yes, etc., etc. So, here is your Python implementation of the same. You'll notice that we actually have two base cases, right? Perhaps I should back up a bit. You'll notice that this is a recursive algorithm, right? The thing about the binary search, once you have divided the search space, you can apply the exact same algorithm again to the reduced search space. This makes it a recursive algorithm. It's not the only way to do it. This way of doing it will actually, well, it'll use more memory, because if we remember, applying a slicing operation will create a duplicate of the sliced items in memory. This is actually guaranteed to use no more additional memory than the input array was. But, you know, it is what it is. We apply binary search recursively on the section of the array that we're interested in. And I know I'm saying arrays instead of lists, but deal with it. We've got two base cases for this recursion, right? In the first case, if there are no elements left in the list that we are searching, that is to say, if the list is empty, it cannot possibly contain the element we're looking for, therefore we return false. If the array contains just the one element, we simply return the result of a Boolean test to see if that element is the thing we're looking for. Right? It's technically redundant to say, if L at 0 is equal to E, return true, else return false. Anytime you've got if X, return true, else return false, just return X. Right? It's simpler. So, do we need both of them? What do you guys think? Do we need both of them? No. Why?
If the length is equal to 1 is unnecessary because the below algorithm would have figured that out anyway.
Well, that's true. Because that's going to be the midpoint anyway, right? So you'll hit it here anyway. That's true. But also, if we have an array that has only one element, right, and we perform this method on it, we will end up passing an empty array into the next iteration anyway. So we'll hit this case on the next recursive iteration, and we don't need to test explicitly for an array of length 1 here, right? In general, we have a redundant base case here. Did you have a question? So here's the question. The question is, would that not speed it up? So here's the question. Here's the question you have to answer, right? How much additional work is introduced by testing that condition? And is that greater than making one additional recursive call? Adding code here, that code has to be run every single time you make a recursive call, right? So, depending on how many items you're sorting, the more items you're sorting, the more that statement has to be run. Yeah, sorry, that's what I meant, yeah. So, versus, you always, and actually not even in most cases, have to make one more call to the recursive function, right? The number of extra calls to the recursive function is actually constant, no matter how many items you're searching. So, I would say, yeah, actually you want to get rid of it, right? Make sense? Reduce the size of the inner loop, my friend. Reduce the size of the inner loop. Okay, any other questions? Okie dokie. I won't be in my office today because I forgot my laptop charger, so I'll have to go home and work from home. So.